Hello everyone, welcome to Agrawal tutorial. In this video lecture, we will discuss about the concept of convolution. It is one of the most important topic of integral mathematics, as the convolution and its related operations are used widely in the area of science and engineering, especially in the field of signal and system analysis, digital image processing, etc. Okay, so in this lecture, first of all, we will start with the definition and some basic properties of convolution, and then try to understand the concept through graphical visualization. Okay, so let's begin and try to understand what the convolution is. So basically, convolution is a mathematical tool which is used to calculate the output of LTI system, that is linear time invariant system, when the input and impulse response of system is known to us. For example, consider a linear time invariant system with impulse response given as h of t and x of t is an input signal applied to the system. Then the output of the system, say y of t, will be equal to the convolution of the input signal and the impulse response of the system, that is y of t equal to convolution of x of t and h of t. Okay, so let us see the definition of the convolution. So by the definition, if x of t and h of t are two functions such that they are piecewise and continuous, then their convolution is given by integral 0 to t x of tau into h of t minus tau d tau for all t greater than 0. Please note here that the convolution between two signals or functions is represented by asterisk mark, which is also known as convolution operator. For example, if the functions are given as x of t equal to e raised to the power t and h of t equal to t, then by the above definition, their convolution will be given as convolution of x of t into h of t is equal to integral 0 to t e raised to the power tau into t minus tau d tau. Please note here that we have replaced the original parameter t by tau, and so the t which is now in the integration does not represent the time domain. So we get e raised to the power t replaced by e raised to the power tau. Similarly, t is replaced by t minus tau. Now by solving the integration, we get the convolution of x of t and h of t as e raised to the power t minus t minus 1. To understand the concept in a better way, let us go through the graphical interpretation of the convolution. For this, let us consider the impulse response of a LTI system h of t as given below function and input xt as this function. Here h of t is a step function having amplitude of 2 and varying from 0 to 1. Similarly, xt is another function having amplitude of 3 and varying from 0 to 2. Now, let us try to find the convolution of these two functions. So, by the definition of convolution, the convolution of x of t and h of t is given by integral 0 to t x of tau into h of t minus tau d tau. And what does this represent? As we know that the integration of multiplication of two functions represents the area of overlapping between two functions. So, this term represents the overlapping area between x of tau and h of t minus tau. So, basically, we have to find the overlapping area between x of tau and h of t minus tau. Okay, so let us find it. So, the first step is convert the variable from t to tau. And do you know why we do this? In order to avoid any confusion between the integral variable and the limits. So, let us replace the variable t by variable tau in the function h of t and x of t. Okay, so our second step is we have to find h of t minus tau signal. Let us see how we can find this. First of all, we will multiply tau by minus 1. So we get h of minus tau. And what is the effect of multiplying tau by minus 1? The signal gets flipped along the vertical axis. So, we get the flipped signal h of minus tau as this. Next, we will add time t to minus tau so that we get h of t minus tau. And what is the effect of adding time t? The signal gets shifted to the left by time t. So, we get the shifted signal h of t minus tau as this. So, after shifting, now the signal starts from t minus 1 and end at t, as previously it was from minus 1 to 0. Okay, so now we have h of t minus tau and the input as x of tau. Now, by the definition, convolution is the integration of these two over a time period from 0 to t. And we have to find the overlapped area between these two functions over the time period from 0 to t. Okay, so let's do it. So these are the two functions and we have to find the overlapping area between these two. For that, first of all, we need to find the regions where the overlapping occurs. So, let us find the overlapping regions. Case 1 is when signals are like this. Now, in this situation, that is, when t is less than 0, clearly it is looking that no overlapping occurs as the signals are far apart from each other. So for t less than 0, no overlapping occurs. Now let's move the signal h of t minus tau closer so that it will start overlapping x of tau. So in this situation, the signal starts overlapping each other. So the region where this happens is when t is greater than 0 and t minus 1 is less than equal to 0. So for t greater than 0 and less than equal to 1, overlapping occurs. Okay, now let us further move the signal h of t minus tau closer such that t is less than 2 and t minus 1 is greater than equal to 0. So, in this region also overlapping occurs. So, for t greater than 1 and less than equal to 2, overlapping occurs. On further moving the signal such that when t is greater than 2 and t minus 1 is less than equal to 2. Here also, that is, in this region also, it is looking that overlapping occurs. So, for this region also, that is, for t greater than 2 and less than equal to 3, overlapping occurs. Now, on further moving the signal such that when t minus 1 is greater than 2, clearly in this condition, no overlapping occurs. So, these are the all possible conditions of overlapping and non-overlapping regions. So, we have got the overlapping regions. Now, we need to find the area of overlapping in these regions. Okay, so let's find it. So, our first region is when t is less than 0, as no overlapping occurs here. So, the resultant area we get as 0. So, write y of t equal to 0. Next reason is when t is greater than 0 and less than equal to 1. Here, in this region, overlapping is occurring. So, the resultant area of overlapping can be found out by integrating the overlapping area from 0 to t, as the overlapping is occurring only from 0 to t. So, we can write overlapping area y of t equal to integral 0 to t 6 dt. 6 is the amplitude multiplication of two signals. So, on integrating this, we get y of t as 6t. Okay, let us take the next reason, that is when t is greater than 1 and less than equal to 2. As the overlapping is occurring in this region also, so just as previous one, we need to find the resultant area using integration. So, we can write y of t equal to integral t minus 1 to t 6 dt. Limits of integration here are from t minus 1 to t, as overlapping is occurring from t minus 1 to t. So, on integrating, we got y of t equal to 6. So, yt is equal to 6 for this region. Repeating the same process for this region also, that is t greater than 2 and less than equal to 3. Here, the limits of integration are from t minus 1 to 2, as overlapping occurs in this region only. So, the overlapping area y of t is equal to integral t minus 1 to 2 6 dt. On solving this, we get yt is equal to 18 minus 60. So, we get yt is equal to 18 minus 60 for this region. And finally, for this region, that is t greater than 3, as no overlapping occurs in this region, y of t remains 0 for this region. Okay, so we have find the resultant of integration, which is nothing but is the convolution of given two functions. So, we have got the convolution of these two functions. So, now let us plot all of these in a graph. So, for t less than 0, y of t is 0. So, we get nothing, that is 0. Now from 0 to 1, y of t is equal to 60. That is a straight line. And what will be the upper limit and lower limit for this straight line? By putting t equal to 1, we get yt is equal to 6. And for t equal to 0, yt is equal to 0. So, we got a straight line varying from 0, 0 to 1, 6. This one. Okay, take the next reason, that is when t is greater than 1 and less than equal to 2. Here we have got yt equal to 6. So, its plot will be this. That is a straight line parallel to t-axis with amplitude 6. Similarly, for t greater than 2 and less than equal to 3, yt is 18 minus 60. This is also an equation of straight line, but with negative slope. That is, at t equal to 2, we get yt is equal to 6. And at t equal to 3, yt is equal to 0. So, we got the plot as a straight line varying from 26 to 30 as this. And finally, for this region t greater than 3, as no overlapping occur here as well, the plot remains 0 after t greater than 3. So, this is the convoluted signal we have got by the convolution of given two functions xt and ht. Okay, so let us quickly go through some basic properties of the convolution. Some basic properties associated with the convolution are: first one is commutative property, according to which convolution of f with g is equal to convolution of g with f. That is, integration 0 to t f of tau into g of t minus tau d tau is equal to integration 0 to t g of tau into f of t minus tau d tau. This means that we can take any of the given function as first one and convolute it with the other one. We will get the same result. Okay? So, next is associative property, according to which convolution of f with convolution of g and h is equal to convolution of f and g with h. Next is distributive property, by which convolution of f with g plus h is equal to convolution of f with g plus convolution of f with h. Next is multiplication by constant property, by which if a constant, let say c, is multiplied by convolution of f and g, then we can also write it as c into f convolve g or f convolve c into g. Hope that you have now understood the concept of convolution. Please like, share and subscribe our channel. Thank you.